I'd like to thank the organizers for inviting me here, and I'd also like to thank the Simons Institute for making my trip here possible. It's great to be here and to be giving this talk. So this talk is about polynomials, and I've not seen much of polynomials in this workshop so far. It's because it's not exactly representing polynomials in this way, but of course it's related, and which is why I'm talking about it here. So this is joint work with Nitin Saurabh. The term enumerator polynomials there is just something that I made up, and let me start off by explaining what I mean by this. So let me start with an example which is very well known to all of us, Hamilton cycles. The typical problem would be that there's an input graph. The object of interest is Hamilton cycles. If you ask whether the graph has such a cycle, well, this is an NP-complete question. If you ask how many Hamilton cycles there are, then this is a sharp P-complete question. And now one could also ask for an explicit description of all the Hamilton cycles in the graph. So there could be just too many cycles, so of course an explicit description will have to put them together in some form, and what we would ask for is an enumeration of them in some symbolic way. So in particular, if I have a new variable for every edge, I can construct a monomial for every Hamilton cycle which just multiplies the variables belonging to that Hamilton cycle. Pick any cycle, look at the edges on that cycle, look at the variables appearing on those edges and multiply them. That's one monomial. Add up all these monomials. So we get a polynomial, and this polynomial, well, it has all the information that one could possibly think about the Hamilton problem. So therefore, clearly we would expect this polynomial to be very hard to compute. Okay? So just in case this notation is a bit unfamiliar, as an example, I've listed out a few Hamilton cycles and the corresponding monomials that they generate. Yeah. So the point is that this, as a polynomial, this must be a very hard polynomial, but then what is the computation model we're talking about when we say that the polynomial is hard? So for this, let me quickly flash this slide, which I use all the time to describe circuits. So we're going to talk about arithmetic circuits. These are directed acyclic graphs. This graph is directed, all edges go up. And at the leaves, we feed in either field constants or variables, which are, of course, polynomials of the most simple type. And at intermediate gates, we are processing these polynomials, either adding them together or multiplying them together and producing more and more polynomials. And finally, there is one designated output node. Whatever polynomial it computes is computed by this circuit. So, well, such a circuit would compute one polynomial. We would be interested typically in families of polynomials growing with n. So we'll talk about a circuit family computing a polynomial family. And we are only interested in polynomial families which are reasonable. Reasonable in the sense that the nth polynomial in the family has not too many variables. The number of variables is polynomial in n. It does not have too high degree. The degree is also polynomial in n. And it's easy to see that the Hamilton cycle family certainly satisfies this. At the nth polynomial has degree n, and it has only n square variables, one for every edge in the graph. So we'll only be looking at such polynomial families. These are what we call P families of polynomials. And now one could ask, how big is the circuit that computes this polynomial? So the obvious notion is polynomial size computable. If there is a family of circuits of polynomial size which computes this polynomial family, then that's great. And that's what Valiant called P computability when he first defined this class. And he also had this notion of P definability. So P computability is like the algebraic analog of P, and P definability is the algebraic analog of NP. So here's a very formal description of it, but even if you don't want to see the formal definition, it's fine. These are just algebraic analogs of P and NP. And of course, Valiant didn't call it that, but now we call them VP and VNP. Valiant's analog of P and Valiant's analog of NP. So it's clear that the Hamilton cycle polynomial is in VNP. It's very easy to see this. And in fact, it is hard for VNP. So it's one of the hardest polynomials out there. That's also not a surprise. But at this point, maybe I should also say that in this model, I have not even described how one would say that something is hard. So I need to specify what is the kind of reduction that we're going to use. And we're going to use projections. So projections is something that we have seen before. I have the slide, so let me go through it again anyway. Here is an example polynomial, G, which looks at 4 variables and computes this. And now here's a list of polynomials which I say are projections of G, because I can obtain them by simply instantiating each of the variables in G by either one of these variables or by a field constant. So I just do a substitution and this polynomial pops out. Then I'll say that this is a projection of G. Here are examples which are not projections. For instance, there is no way I can get the polynomial y1 square y2 out of any substitution here, because substitution is not going to increase the degree. There's no way I can get this polynomial out of G, because substitution cannot increase the number of monomials. So projection is just talking about substitution.
So you're restricting your substitutions to either variables or constants, or you're allowing affine linear?
So for now, I've restricted it to variables or constants, but later we will also talk about affine forms. It's not a major distinction. So right now, by restricting it in this way, I can say this thing here, that F is a projection of G if a circuit for G can be used to compute F without using any extra gates. No extra operations of addition and multiplication. You may have lots of wires which reroute the variables of the polynomial you're interested in into the inputs of G, but you don't have to do any more computation. So that's a projection. And I may also, I will also need to talk about poly-sized projections as opposed to projections. This is important because we are talking not about individual polynomials f and g, but about families of polynomials. So if I want to say that this entire family f is a projection of the family g, well, the nth polynomial here I can write as a projection of some mth polynomial in the new family. That m should not be too large compared to n. So I don't have to go too far away in the target family. So that would be a polynomial projection. So this is a pictorial representation, a circuit for G, which has its own inputs, and I put it into a box in which there are a few additional wires and field constants, but nothing more. And the wires route the variables of f, and I end up computing f. So this is in general, this is a p projection, and if this m is polynomial in n, then it's also, in general, that's a projection. If m is polynomial in n, it's a p projection. So with this notion of reductions, talking about when one polynomial family is easier or harder than the other, we know that the Hamilton cycle polynomial is in fact complete for VNP. And Hamilton cycle polynomial was an example of what I call an enumerator polynomial. The monomials of the polynomial explicitly list out all the Hamilton cycles in a complete graph. And now, because in the complete graph we have introduced a new variable for every edge, by instantiating these variables, we can pull out the Hamilton cycles in any graph that we want. So what other enumerator polynomials are there that are hard like this? Well, there's a whole series of them. In particular, here's one example, enumerating all the cliques. Again, you start with a complete graph, and for every subset of vertices, you multiply the variables corresponding to edges in that little induced subgraph. So there's a monomial corresponding to a clique. For every clique, there is such a monomial. Remember, the variables are sitting on the edges of the graph, not on the vertices. So here's another way of writing the clique polynomial. Each monomial can be described not by a set of vertices, but instead by a set of edges. You can look at a subset of edges, but that edge set must satisfy this property, that it describes a clique and then maybe some isolated vertices, and then we multiply this. So this formulation is what's going to be important to me later on, so that's why I've put it up here. So this polynomial is also complete for VNP with respect to P projections. Another example of an enumerator polynomial is enumerating perfect matchings in bipartite graphs. So just start with a complete bipartite graph K and N, and for every perfect matching you have a corresponding monomial, and you add them up, and this is in fact exactly the permanent. So even in this algebraic complexity setting, it is hard for VNP, but this hardness, as we know, is only when the characteristic is not 2. Okay, so we have some examples of polynomial families which are hard in the algebraic computation setting. Now here's another polynomial which looks very much like the preceding polynomials. It enumerates cuts in a graph, in the cut enumerator polynomial. So start with the complete graph, look at every partition of the vertex set into two pieces, A and B, and then multiply out the variables on edges which go across the AB cut. So for every cut I have a monomial, and there are no other monomials. So as an example, if I'm looking at the third polynomial, so I have the graph K3. In that, the partition must have either is a trivial partition, 0 on one side and all 3 on the other. That's going to give rise to this monomial. Or it has a partition where one side has a singleton and the other side has 2 elements. So this monomial comes out when vertex 1 is on one side and 2 and 3 are on the other side. And similarly for the other two cases. So this is the cut polynomial for K3. Now you have a cut polynomial for K4, K5, and so on. So this looks very much like the other polynomials that we saw before this, that it's just enumerating these combinatorial objects. And it's not very hard to see that it is in VNP. So I started off saying that this is a remarkable enumerator polynomial. So what's so remarkable about it? What is remarkable about it is this result which was shown by Peter Bergesser 16 years ago. Over the field GF2, this polynomial is neither in VNP nor VNP hard with respect to P projections, unless the PH collapses to the second level. So it's a conditional result, and it's only over the field GF2, but it's still very interesting because the previous polynomials that we listed out were complete for VNP over every field. Well, not all the polynomials. Permanent was not complete over characteristic 2. So now here, the permanent was not complete, but this thing is saying something more. It's saying that it is not in VP either, whereas the permanent we knew was in VP. So this polynomial is an intermediate polynomial, unless languages which are in mod 2P, parity P, have polynomial size circuits. That would also imply that the PH collapses to the second level. So this is something unusual about this polynomial. And so let me briefly say a few words about intermediate complexity. In the Boolean world, we know that there are intermediate problems. Ladner's theorem from many, many years ago tells us that if P and NP are distinct, then we can find a language which is in between P and NP complete. And an exact analog of this is also known in the algebraic world. Bergesser himself proved this in 1999, that over every field, it doesn't matter which field you're looking at, if VP and VNP are distinct, then there is a polynomial which is in between, it is definable, but it's not hard for definable polynomials, and it is not computable. But the problem with these two statements and their proofs is that basically the proof demonstrates the existence of such a language or such a polynomial. The existence is demonstrated using diagonalization. So typically that the problem which is intermediate is not very explicit, not very nicely defined, whereas the cut polynomial was so explicit. So we don't really have many examples of explicit languages or polynomials that we know are intermediate. Even in the Boolean world, the language functions that comes out of Ladner's construction is sat with some holes punched in. So there is a kind of natural looking definition, but where do you punch those holes? That's not easy to describe. Whereas the cut polynomial is very easily described. So in order to get this explicit representation, we need to assume a little bit more. So the fact that this cut polynomial is intermediate does not just follow from the assumption that definability and computability are different. We also need an additional assumption that parity P is hard for poly-size circuits, which would also imply that definability and computability are different. So with an additional assumption, we can come up with these explicit polynomials which are provably intermediate. And this was a result only over GF2. It's a very natural question to ask whether such a result also holds over other fields. It turns out that cut polynomial itself is in fact VNP complete over reals. So the arguments used to show that it is intermediate were very, very specific to this field. Over reals, Nicolas de Ruguy-Alter showed this a few years ago. You could also look at other fields. So other finite fields, Peter Bergesser completely answered this question using the cut polynomial itself. Fix any field, finite field of size q, and then you just tinker with the cut polynomial by raising every variable there to the power q minus 1. So from Fermat's little theorem, we know all this does is to take zeros to zeros and non-zeros to 1, and then you can use the arguments that worked over GF2. So what Bergesser showed was this. For every prime power q over the field fq, this polynomial which I have listed out here, it's certainly in VNP, and if counting modulo p is easy, then it is intermediate. So, sorry, unless it is easy. This is intermediate, sorry. Yeah? So if counting modulo p is something that we don't know how to do efficiently, even in a non-uniform setting, then we can prove that this cut polynomial is neither hard for definability nor polynomial computable. So this was what Bergesser showed in 1999, and since then these were the only known intermediate complexity polynomials. So what we do is to come up with some new intermediate polynomials. And so one way to see, because the definition of at least some of our intermediate polynomials looks a bit weird, so maybe we should try and examine where did that intermediateness of those polynomials come in from. So the Hamilton cycle polynomial or the Clique polynomial, they were not intermediate, they were hard. And they were hard because their monomials encoded the weights of some hard to find combinatorial object. Now this itself is not a very satisfactory explanation because cuts are also not very easy to find if you're looking at large size cuts. But basically it says that there's something to do with this encoding which we have to carefully doctor. So what we do is that we put more information into the encoding. Each monomial does not just talk about maybe a clique exactly a clique, but it has some auxiliary information also. And that auxiliary information is thrown in to make sure that the resulting polynomial is not hard. But then you have to be careful. If you throw in too much information, it may become too easy. So we just have to make sure that we put in the right amount of information so it comes down from VNP hardness but stays above VP. So the starting point is always VNP hardness. We're not starting from VP and going up, but starting from VNP and coming down. And the question is how to put in this extra information. Using this approach, we come up with intermediate polynomials which are based on encoding these combinatorial objects. Cliques themselves, but encoded in a different way. Vertex covers, closed walks, three-dimensional matchings, as well as three satisfiability. So I'm going to run you through the definitions of all these polynomials and then just sketch very briefly the intermediateness proof for one or two of them. And in particular, the definition of clique, let me go over it a little more in detail, because there is an old definition of clique which we know is hard. And now here's a new definition of a clique polynomial which is not hard. So in the old definition, I'm using this formulation. Look at every subset of edges. If that subset of edges forms a clique and an isolated vertex, then throw in the monomial corresponding to it. In my new definition, which this nomenclature comes from my co-author, he says it works equally well for clique or independent sets, so CIS. You take every subset of the edges and don't enforce this condition. Whatever the subset, you throw in the corresponding monomial, but now you throw in auxiliary information into the same monomial. So now we have some new variables. These are variables which sit on the vertices of the graph, not on the edges. So I throw in all the edge variables from this set, and then I also multiply this monomial by the vertex variables corresponding to those vertices which are touched by this set. Now if you look at this composite monomial, I mean, of course it has the information you need to check whether this forms a clique or no. But in particular, the degree in the y variables is an indicator of whether or not this is actually a clique. If you're touching k vertices so that you have k y variables here, then you would expect to have k choose 2 x variables on the other side. So we just remove an explicit condition from the subset, but then throw in auxiliary information using auxiliary variables, which gives you back that information. Now notice that in this process we have thrown in a whole lot of garbage into the polynomial. So we would have been interested only in cliques, but now here we have a lot of non-cliques also. So the cliques are still there, but then there are non-cliques. So as an example, in the 3-vertex graph, T could have been the empty set. It contributes monomial 1 in both the cases. T could have been the clique on size 2, in which case in the old definition it would have just given the monomial x12. Now I get x12, y1, y2. Okay. It could also have been the entire edge set, in which case in the old polynomial I would have gotten these 3 x variables, and in the new polynomial I get the 3 x variables as well as the 3 y variables. But here are the kind of garbage monomials. So I have an edge set with 2 edges. It would not have qualified in the old definition at all, but in the new definition this also contributes a monomial with those 2 edges, but the 2 edges touch all 3 vertices, so I have all 3 y variables. So I've thrown in extra monomials, and the idea is that by throwing in these extra monomials, you can use them somehow in the computation to make the overall computation easier. The idea of throwing in stuff which eventually either cancels out or is irrelevant or whatever, so that's going to make this new polynomial easier than the hard polynomial. At the same time, it still has information about a clique, so it cannot become too easy. That's the idea. So this is our definition of the clique polynomial. And this is for GF2. For other fields, exactly the same thing, but you just raise this to the power q minus 1 if you have a finite field of size q.
So could you just explain this 1, 2, 2, 3 is somehow clique plus isolated vertices?
No, so this is not a clique plus isolated. So this is the garbage term.
Oh, that's not there.
Yeah. So in the original definition, we only wanted edges which formed a clique. In the new definition, we are willing to handle any subset of edges, whether or not it forms a clique. So this is something which would not have appeared here at all. And here it appears with this y information. Yeah. So as I said, over other fields, we can again use the same trick. So in fact, in the subsequent slides, I won't even describe the other fields version. Let's just work over GF2. What about the SAT polynomial? So we look at 3 SAT, 3 satisfying satisfiability of 3 CNF formulas. So fix n, we are looking at formulas over n variables. So there are the n variables corresponding to those variables in the formula itself. And we also introduce 8n cube new variables which correspond to potential clauses. So variable, one of these variables denotes whether that clause is actually present in your input instance. And now, So if I were given an actual formula, I would want somehow a sum over all satisfying assignments of that formula. So instead here what I do is I just look at all assignments, pull out the variables which are 1 in that assignment, and pull out the clauses which that assignment satisfies. So these are just potential clauses because I don't even have an input formula. Just list out all the clauses which this assignment can satisfy. So now when we instantiate y with a specific formula, the clauses which are present or no, then this part will kill assignments which are not satisfying. So again, it has, for any specific formula that we would be interested in, this polynomial will have information about the satisfying assignments of that formula. But because we have thrown in some sense, garbage, it's going to become easier to compute. Okay. The closed walk polynomial. So for this, maybe I should briefly describe. What do I mean by a Clow? A closed walk is, it's basically a path in the graph, but not necessarily a simple path. You're allowed to self-intersect, visit vertices more than once, even use edges more than once. But we are going to impose one condition, which is that the smallest vertex in the path should not be visited more than once. The other vertices, there are no restrictions. The smallest vertex should not be visited more than once. Other vertices, there's no restriction. So this is what we call a Clow, and based on Clows, now we have this polynomial which says, look at every Clow, every closed walk in the complete graph, a closed walk of length exactly n. By length I mean it has exactly n edges. It may touch fewer than n vertices or all n vertices. If it touches all n vertices, it would be a Hamilton cycle, but in general it could be something else. For that Clow, you look at all the edges which are used in it, multiply out those variables. Now this part in fact need not even be multilinear because you could be using the same edge more than once. So you produce some monomial here which may not even be multilinear. And then you throw in this indicator part. We have the new vertex variables, and you throw in every vertex variable the vertex variable for every vertex which is touched by that Clow. So now again you can see where Hamilton cycles sit in this. So a Clow which is actually a Hamilton cycle will give all n y variables out here, and it will give something multilinear out here. And directed. So all the Hamilton cycles are sitting in there, but then a lot of non-Hamilton cycles are also sitting in with appropriate indicators. So the presence of the non-Hamilton cycles makes the polynomial easier than VNP hard, and the presence of Hamilton cycles makes it hard, so it is not in VP. Okay, I had this example. So here's an example of a Clow of length 5 or 6, 1 to 2, 2 to 3, 3 to 2, 2 to 3, 3 to 1. And that's going to give rise to a monomial which has degree 5 in the x variables. x12 is used once, 23 is used twice, so I have x23 square, x32 is used once, and x31 is used once. But then I have the y variables, and the y variables are not thrown in with repetition. So even though a vertex may be visited more than once, it's very important for a proof later that the y variables, only one copy of each, at most one copy of each variable is thrown in. Similarly, I could have a Clow which looks even more simple. From 1 you go to 2 and you just keep looping around there and then come back. That gives rise to a monomial like this. So these are all garbage monomials which turn out to be extremely useful later on. We have a similar definition for vertex cover. By now it's looking very similar, so maybe I should just skip this. A set of vertices, the indicator set for that set, and then for the vertex set, and then the edges which are touched by that. We have a similar polynomial for three-dimensional matching. You look at three-dimensional matchings in a complete tripartite graph, and so instead of looking at matchings here, I'm just looking at any subset of the hyperedges and putting in the corresponding monomials. Okay, so I listed out 5 new polynomial families, and I am claiming that all 5 of these are intermediate. Why exactly are they intermediate? So very roughly I have already said it's because of the garbage monomials make it easy and the hard monomials make it hard. But how do you formally go around proving this? Well, we use exactly Burgess's strategy. It just needed a little bit of adaptation because our encoding was different. So what we need to show is that for each of these polynomials, cut is what Burgesser himself showed and the others we showed. For each of these polynomials, we need to show that it's in VNP, of course, otherwise we have nothing to go by. Now this part is easy in all these cases, so I won't even talk about it. We also need to show that these polynomials are easy, and the definition of easy which is sufficient here is that over GF2 they can be evaluated in Boolean P. Okay? I have a polynomial time algorithm which, given the values to all the variables in the polynomial, spits out the output value. Not in an algebraic computation model by an ordinary Turing machine. So in that sense, this polynomial is easy. And if it is easy in this sense, then it cannot be hard in the algebraic sense. Okay. So once we show that it is easy, then a VNP hardness would imply that parity P or mod 2P also has small circuits. And that would contradict the assumption that we are starting off with when we want to show that something is intermediate. For the last part, we need to show hardness. We need to show that this polynomial is somehow hard to compute, and therefore it's not going to be in VP. If it is in VP, then the same bad consequence should happen. In order to show this, we want to use the fact that the monomials of H are encoding solutions of a Sharpe-Hard problem. So that's where the counting comes in again. The underlying problem is Sharpe-Hard via parsimonious reductions. Okay. So if you look at these two steps, they kind of seem to be completely in opposition to each other. On the one hand, we're saying that H is easy to evaluate. It's in P. On the other hand, we're saying it's not in VP. And this is, in fact, the whole point about the difference between the algebraic computation model and normal computation, that algebraically, if you want to symbolically carry forward the entire polynomial, we don't know how to do it, and we don't expect to be able to do it. But on the other hand, if you just want to evaluate it at specific points, then that is easy. So let me show why SAT is intermediate following that template. As I said, the membership part I will not show at all. Membership in VNP is trivial. Why is this polynomial easy? Okay. So I said we need to show that given specific values to the variables, I can evaluate this in Boolean P. If a 0-1 assignment is given to all the variables, then notice that I want to sum over all assignments. And each assignment is going to contribute either a 0 or a 1 to the sum. So when will it contribute a 1? For an assignment to contribute a 1, it must be the case that whenever an x variable takes the value 0, A should also be 0 there, because otherwise the monomial gets killed. Similarly, whenever a clause takes the value 0, it must be the case that that assignment does not even satisfy this clause. So the moment we are given values to x and y, some bits of A are completely fixed. In order that A is able to contribute to this sum, some bits of A have to be fixed in a certain way. And the remaining bits of A are unfixed. You can change them in any way. So therefore, the total sum is exactly 2 raised to the number of unconstrained bits. So this tells us that this is easy. Right? In fact, because we are doing computation modulo 2, you just want to know whether there are any unconstrained bits still left. If you're looking at another field, then you will look at this sum 2 raised to the number of bits modulo P. Why is this hard? Well, to see that it is hard, we start off with this polynomial and pull out a bivariate polynomial out of it. Given any real instance of 3CNF SAT, so we're given an instance F which has n variables and m clauses, I'm going to transform this formula by setting all the y variables to t. T is a new variable. And I'm going to set, not all the y variables. All the y variables corresponding to clauses which are present, I set to t. The other variables I set to 1, so they play no role. And the x's play no role in any case. So I get this, not bivariate, but univariate polynomial t in t. And every assignment A contributes a term t raised to the number of clauses which are actually satisfied by A. And since we are interested in satisfying assignments, we want this exponent here to be the degree. So we're just looking at the coefficient of t to the n. So it's not that the value of this polynomial gives us what we want, but a particular coefficient gives us what we want. If this polynomial were easily computable, then we would be able to do coefficient extraction also. So this is the spirit in which we can show that all those 5 polynomials are intermediate. And I do have slides for 2 more of these, but I think I will skip them. Why? So the typical template is to show why it is easy by saying that the easy part boils down to something completely trivial, and the hard part is to show where the monomials are encoding these hard objects. In the case of Clique, it was a bivariate polynomial. In the case of SAT, it was univariate. In the case of Clow, it was again bivariate, and so on. So let me stop with that topic for now. Sorry, I should go back. Yeah.
So you said previously that for this problem, for the closed works, you need for the y variables to be
to appear only once.
Right.
Yeah.
So does it mean that if you have the multiplicities corrected, then it would be in?
Okay. So for that, maybe I should look at the hardness part. I want to say that this polynomial actually encodes Hamilton cycles, and for it to encode Hamilton cycles, I'm going to convert this polynomial to a bivariate polynomial. And in that bivariate polynomial, the coefficient of z to the n, t to the n is going to be the number of Hamilton cycles. Now, if I throw in y variables with multiplicity, I may get t power n without having a Hamilton cycle. So it's important there. Okay, so actually I have results of 3 different flavors which I want to present, and the first one was about intermediate complexity. Let me now jump to the next one, which is enumerating graph homomorphisms, and here we have something which is very different from intermediate complexity. So homomorphisms we have seen a lot in this workshop, so we know what they are, and the typical questions are, is there a homomorphism, count how many, approximate how many, and we are going to ask again the question of symbolically enumerating all the homomorphisms. So the so-called enumerator polynomial that we construct for this looks something. Given 2 graphs G and H, I have variables sitting on the edges of H. So I'm thinking of G as fixed, and that's why in the abstract I said this is homomorphisms from the left. H has variables sitting on every edge, and as I instantiate these variables, I get different target graphs H. So now let's look at a polynomial corresponding to homomorphisms from G to H. For each homomorphism phi, I just look at the image of every edge and take the corresponding edge variable, multiply them out into a monomial. So this is very similar in spirit to the previous polynomials that we saw, but of course the underlying object here is not hard. So we don't expect this to be VNP hard or VNP intermediate. The question is now how easy is it? And what we show is that it exactly characterizes VP. So this is our definition of the polynomial. Again, we need families. So we need families of graphs to describe families of polynomials, and the families of graphs should again grow reasonably. The nth graph should have number of vertices which is polynomial in n. Okay, an example here. Look at a homomorphism like this. It gives rise to a monomial like this. I think we've seen examples. So maybe this I can skip. The monomials are just encoding the homomorphisms. Now there's one notion that we use in our result, which is that of rigid and incomparable graphs. So a graph is rigid if it has no non-trivial homomorphism to itself. Most graphs are rigid. A pair of graphs is incomparable if there is no homomorphism from A to B or from B to A. Most pairs of graphs are incomparable. And we will use these in a gadget construction. So here's the graph family. I'm going to describe now a graph family. I have to describe Gn and Hn, and then we just look at homomorphisms from G to H. So the nth graph G, I start with a complete binary graph with exactly n leaves. Of course, n may not be a power of 2, so take the smallest next power of 2. Start off with a binary tree with exactly that power of 2 leaves, and we are fixing 3 graphs which are known to be rigid and pairwise incomparable, and we plug in those graphs into this tree. So at the root I plug in the graph I0, and then at subsequent alternate levels I1, I2, I1, I2, and so on. Each of these graphs has some designated attachment points. So I use those attachment points to connect the gadgets to the next level or to the parent. And then I also have this bound on the size of whatever graphs I fix, their size, total size together is C. So I go back to the original edges of the tree and I stretch them so that they are all longer than C. So this is my family Gn, complete binary tree, each node inflated into one of those gadgets, and each original tree edge stretched into a long path, and the family H is just the complete graph on an appropriate number of vertices. What we show is that homomorphisms from G to H in this family is exactly complete for VP, for polynomial time computability of polynomials, and this completeness is with respect to P projections. In fact, there's a slight modification of that where instead of the graph being a binary tree, if I start with a simple path, then I get completeness for a slightly smaller class, presumably smaller class, which is polynomials computed by branching programs. But I think I won't talk about this.
What's the degree of this polynomial?
Of the homomorphism polynomial?
F?
Yeah, so it's the number of edges in G.
So 2 to the log n.
Yes. Because every edge is contributing one variable out there. Okay, so we started off with a different kind of enumerator and we got VP completeness, and it's a fairly natural question to ask, what's the big deal about this? Well, to us the big deal was that this is the first natural complete polynomial for VP. So as a computation model, polynomial size, polynomial degree circuits, it's extremely natural, but there were no natural polynomials known for this class. So there were some generic polynomials known that the circuit class is defined based on circuits. So you take a canonical circuit computation and pull out a family out of it. Of course, that would be complete. But for most reasonable complexity classes, you expect that problems arising from various domains turn out to be complete for them. And there was really nothing known to be complete for VP with respect to polynomial projections. If you allow slightly larger projections, quasi-polynomial size projections, then it's been known for a long time. Wayland showed it, I think, in 79, that the determinant is complete for VP. But it does require this quasi-polynomial blow-up. We don't know whether it can be done with a polynomial blow-up. So the big deal for us was that this is, so there is this caveat. This is almost the first. 2 years ago, with another bunch of authors, we had also shown that some polynomials based on graph homomorphisms were VP complete. But there were many things which were not satisfactory. In particular, either the VP completeness was with respect to oracle reductions, not projections, or the homomorphisms came with caveats. You look at only injective homomorphisms, look at only directed homomorphisms, and so on. So there were various such caveats, and in this result, there's nothing. I mean, the graph families are cleanly described, and we're looking at all homomorphisms. For algebraic branching programs, complete polynomials were known earlier, determinant, iterated matrix multiplication. So here's one more from the homomorphism framework. And one point to note is that our upper bounds, actually, computing the homomorphism polynomial from G to H, they hold whenever G has bounded tree width and H is complete. So in our example, G was bounded tree width because we started with a tree and then we put in these gadgets. And the upper bound holds whenever it's bounded tree width. Okay, so this was the second flavor of the results, and in the next last 5-6 minutes, let me try and describe the third flavor of results, which is completeness with respect to monotone P projections. So P projections were already restrictive enough, and what can get more restrictive? Well, there was this do-nothing reduction talked about, but here that's not what I'm talking about. I'm talking about looking at P projections. They're still, you have wires going all over the place, but you are not allowed to use negative constants. So this makes sense, of course, only if you're talking over a totally ordered semi-ring. So to compute f from G, you take a circuit from G and replace each variable of G by either a variable of f or by a constant. If you replace it by a constant, that constant must be greater than 0. Okay. So we can talk about when f is a monotone projection of G. Now, this makes sense. So all the polynomials that I listed out earlier were monotone. They had 0, 1 coefficients, so the descriptions of the polynomials themselves were monotone. Why would one want to relate them via monotone projections? Well, one goal would be to get lower bounds for restricted circuits, in particular for monotone circuits. So Jukna observed this a couple of years ago, that if somehow we can show that the Hamilton polynomial, which itself is monotone, is a monotone P projection of the permanent. Okay, before I read further, let me just point out that the Hamilton cycle is definitely a P projection of the permanent, because the permanent is VNP hard. But the point is that that projection is not known to be monotone. So we are emphasizing monotone and polysize. Now, if the Hamilton cycle is a monotone polysize projection of the permanent, then we can show a monotone circuit lower bound for the permanent, which is exponential. And this would improve the best known bound over for Boolean circuits. So for Boolean circuits, as far as I know, the best bound is what Rasbarov showed in 85, quasi-polynomial size is required by monotone circuits. Over reals, we know better. So over reals, if this statement were true, that Hamilton is a monotone P projection of the permanent, then it would give a different proof of this known result due to Jeremy-Snare, also from many years ago.
May I ask, for if you, instead of permanent, you want to count the number of perfect matchings, is it still not? I don't
know. So somehow we've been thinking only about permanent, and only after coming here I've been seeing that, looking at perfect matchings in general would also be an much more interesting thing to look at perhaps. So I don't know. So this is why one would even want to ask this question, are there monotone polysize projections? What Groucho showed in response to this comment from Jukna is that any monotone projection from permanent down to Hamilton must have an exponential blow-up. So if you want to write the Hamilton cycle polynomial as a monotone projection of the permanent of a perhaps larger matrix, then that perhaps larger will have to be significantly larger. That's really what this says. So Jukna's idea was that, well, we know that the clique is a monotone P projection of the Hamilton. That's known. And therefore, if you can show this with poly blow up, then a lower bound from clique transfers to a lower bound from permanent. So what we show is that this kind of thing, no monotone projection, we can also show it for some other families. In particular, for two of our intermediate families, Sat and Clow, we show that they are certainly not monotone polysize projections of the permanent. Now, this is exactly the same in spirit to this result by Groucho. These are not conditional results. They're just saying that monotonicity is a real restriction and you cannot do this. In fact, so specifically, if you project down from the permanent to get Sat using only non-negative constants, then the blow-up will have to be 2 raised to square root n. If you project down to Clow, then the blow-up will have to be 2 to the omega n. And more recently, Nitin in fact showed that even to come down to the clique itself, you would need 2 to the square root n. So this completely kills the hope of transferring a lower bound from clique to permanent via this approach, via monotone P projections. So in fact, this was the question which Jukna had raised earlier, but he somehow couched it in terms of the Hamilton cycle, and we can show this directly for the clique. So how do we prove these kind of results? How do we prove that any monotone project? So here, somebody asked earlier about affine versus variable. So here, the statement goes through even for affine projections, provided in the affine combinations you don't use negative constants. So okay, so how do we show this? Basically, we're using Groucho's idea, and then we pick up various results which are known in the literature. So we're going to associate polytopes with the polynomials as well as with the solution sets. In particular, for the permanent, the polytope which we look at is the convex hull of all bipartite perfect matchings. So look at the complete graph KTT. It has t square edges. So let's look at dimension t square, a t square dimensional vector, and look at the 0, 1 indicator variable of a perfect matching. It will have exactly t ones and the remaining zeros. So look at all such vectors, take their convex hull. That's a polytope.
Take the Newton polytope analogy.
Yes. I was trying to not use that word. Okay, yeah. And this polytope can be described with order t inequalities. For satisfiability, also this is also the Newton polytope, which is you look at the vectors of degrees of monomials in the polynomial and then you take their convex combination. So for the satisfiability polynomial that we looked at, we have this polytope in n plus 8 n cube dimensions, but actually the first n bits completely dictate what happens in the remaining 8 n cube positions. Now, Avis and Tiwari have shown that there are formulas for which even, so you want to look at the combinations of satisfying assignments. That's the polytope that you're really interested in for these formulas. Even if you take this polytope and look at its embedding in a higher dimension, to describe that polytope, you would require lots of inequalities. So the extension complexity of the satisfying assignment polytope for some formulas is huge. So now you put these two together, and then there is this step which Groucho showed. If you have a monotone P projection from F to G, then the extension complexity of F is bounded by the size of the projection and the description complexity of G. So that tells us that the satisfiability polynomial, if it has to be written as the permanent, the blow-up must be huge. Because otherwise you would have a small description of these formulas which are sitting here. For the closed sequence polynomial, is the TSP polytope, the traveling salesperson polytope, which is sitting inside the Newton polytope of Clow. The traveling salesperson polytope we know has large extension complexity. Rothfuss showed this a couple of years ago, and therefore it follows that you cannot go get the Clow polynomial from the permanent polynomial, okay, using monotone projections. And okay, I mentioned that Nitin also showed this for Clique. There he needed to use the correlation polytope, which also has these lower bounds. Okay, so to summarize, as I mentioned, there were results of 3 different flavors. We showed that some polynomials are intermediate under complexity theoretic assumptions. We showed that 2 of these families cannot be expressed as monotone polysize projections of the permanent. The blow-up is provably large. And then we came up with enumerator polynomials based on homomorphisms, which are actually VP complete, and is the first natural family that we know of which is complete for VP. So this suggests that with homomorphisms, actually there's a lot more that one could do, because there are also VNP complete variants and so on. And open questions, well, there are many. So intermediate complexity, can we address this question over all fields? Right now we only do it for finite fields, and somehow depending on the field size you have a different polynomial. Can we come up with one polynomial which works on all fields of the same characteristic? We don't even know that. the second question is related to intermediate complexity polynomials, which you can write nicely through the as a permanent, and so on. So these are some questions that we are still looking at. And thank you.
Questions? So, do you know the symmetry group of this natural intermediate, natural polynomial for VP?
No. The graph homomorphism polynomial. No, I don't know.
So, this idea of padding the polynomial, of counting with the extra variables which allow you to throw some garbage like non-cliques, but that shows up in the usual counting problem, where instead of counting proper objects, you're saying, okay, I allow some violations, and then usually in terms of just computing the hardness doesn't change with it. But somehow here, that suggests in a way that VPN is even harder than number P, or what?
It's okay. So separating VNP from VP is necessary to separate P from NP, but to separate P from sharp P also, yes, I would think. My impression is that okay. So I don't know. Is VNP harder than sharp? I didn't think of it that way. To me, it's just that in the algebraic computation model, it's easier to show lower bounds, because you have really tied your hands together by saying that you can't zero in onto individual monom. You have to symbolically carry forward the whole computation. So it should be easier to show that some things cannot be done.
Sure. But the usual counting problem, you throw extra variables, allow penalization, usually doesn't make the problem
Easier. It does not make it easier.
unless you make the penalty so that then you can do the apirasis and things like that. But usually it's just as bad as the original problem. But somehow here it's not as bad.
Okay, I don't have a better answer.
Can't you produce infinitely many examples?
I'm sure we can.
One of the second order definable graph polynomials instead of counting over cliques or independent sets, or your dominating sets or whatever. But formally, if you can do the same thing in your formalism.
No. So we did briefly try coming up with a meta theorem like this, but I think I would also need to specify what is the encoding that I use. So what is the extra garbage that I throw in, and somehow I don't know how that can be made independent of the combinatorics of the specific problem that we're looking at. I don't know as yet. So therefore,
You always list the edges and the vertices to which the edges belong.
yeah. So it's not clear that it's always going to be enough to show intermediateness. To prove this as a theorem, that once you do this, you have, I don't know how to do that yet.
Other questions? Please, so thank the speaker again.
Thank you.